Welcome to Biology Made Easy. Today we are discussing independent assortment of chromosomes or alleles or genes. And this lesson, you will understand it fast and well if you understand chromosome structure, alleles, homologous chromosomes. Please check my lessons on these. Independent assortment of chromosomes, alleles, or genes. You know, if you have these as chromosomes, these as genes on them, this and this are alleles. So this is a homologous chromosome. This is also another homologous chromosome. This can be maternal, paternal, maternal, paternal, homologous chromosomes. So I have two sets of homologous chromosomes here. Now, at the end of Prophase 1, you would have seen that this chromosome, in fact, is being made up of two chromatids with a centromere. So this and this are sister chromatids, and this is a centromere. This and this are sister chromatids and a centromere. And these two are homologous chromosomes. This is also homologous chromosomes. Independent assortment simply means these chromosomes are going to separate during meiosis. This homologous chromosome and this one will separate, not dependent upon how this homologous pair separate. And this independent assortment of chromosomes or alleles, because the chromosome goes with its allele or gene, it starts at metaphase 1 and ends at anaphase 1. Now, this is prophase 1. At anaphase 1, the bivalents, so this and this are bivalents, this and this are bivalent. Bivalents are homologous chromosomes that have paired up. So at metaphase 1, the bivalents, this and this are homologous chromosomes, they pair up at the equator of the spindle. So this chromosome is here, this one is here. These bivalents have paired up at the equator of the spindle. This and this are bivalent, they are homologous chromosomes. They pair up at the spindle. So this one is here and its pair is here. So at metaphase 1, there are two rows of chromosomes. The bivalents pair up. Now, how the bivalents pair up is separate from its pair independently of how the other homologous pairs are separating. And that is independent assortment. So if you look at this one, we can have this kind of pair, or this, or this, or that. Good. We now want to see how we can easily sort out the pairs. So let us just arrange the chromosomes first. And we'll do that for all of them. And then we will see. Okay, so now let's see how this one was done very easily, sorting them. So it is this that you are going to sort out, all right? This chromosome and this chromosome, they are going to separate at anaphase 1. So I have this chromosome can separate and go with this chromosome. Let's just do the tops first, all right? This one and this one will separate, but let's look at this one. This one is going into the same plane with this one, or this one is going AA into the same, not with this one, but with this one, BB. And this one, AA, can go with this one, or this one, go with this one. And then, when we've sorted them like this, they will separate. So once this big A is here, here will be small a, they separate. So here will be small b, so here big A, so here will be small a. We have big B, small b, so this place will be big B, they separate. Here, big B, here, so we have small b here, they separate. Here, small a will be here, so they will separate. Big A is here. Here is small b. So big B, big B. So this is how the chromosomes line up at the equator. And they have lined up the equator like this. That's metaphase 1. That's how we got it. So now we are going to have anaphase 1, where these are going to move to this pole. This is also going to move to this pole. Move to this pole, this moves to this pole. And then we'll go to telophase 1. So, metaphase 1, the homologous chromosomes have paired up at the equator. And anaphase 1, homologous chromosomes separate to opposite poles of the cell. So, we have this chromosome going up here, its homolog coming down. So, we see homologous chromosomes separate, this one up, this one down, this one up, this one down at anaphase 1. And that is what happens in all these. So you have independent assortment of chromosomes because this can go with this, or this can go with that. And so you have either this situation, or this situation, or that situation, or that situation at anaphase 1. So by the time we have telophase 1, the homologous chromosomes have separated. They are at opposite poles of the cell. So we have now 2 nuclei. Telophase 1, you have 2 nuclei. You either have this and that. So this is now telophase 1. We have turned it into telophase 1 now. And this is the situation we have. Now let's look at what happens at prophase and then look at the last result. Now you have prophase 2. And prophase 2, look at it, the spindle is formed at right angles to what was done in prophase 1 up to telophase 1. Now let's get to metaphase 2, right? Now at metaphase 2, the homologous chromosomes line up in a single line at the equator of the cell. So this is this cell, this chromosome and this chromosome line up here. They line up at the equator. This one and this one line up. So you can have this situation or that or that or that. So here I've brought the metaphase 2 here. At anaphase 2, the centromere holding the chromatids break. So this centromere will break and sister chromatids will separate. So I'll have this chromatid here and this one here and this one here. Sister chromatids separate. One A is here, another big A is here. Centromere breaks, sister chromatids separate. So I have another 1B here, 1B here. The same thing happens into this cell. This centromere also breaks. This chromatid goes here. This sister chromatid goes here. And you have this situation. This one is here. This one is here. So I have small a here, small a here. And then this centromere also breaks. This sister chromatid goes here. This sister chromatid goes here. Sister chromatids separate at anaphase 2. So I have this one here, this one here. The same thing is going to happen in all these situations. Anaphase 2, sister chromatids have separated. This and this are sister chromatids, they've separated. This go to this pole, this go to this pole. That's anaphase 2. The same thing is happening all. Telophase 2, the chromatids arrived at the poles, they've thinned out, now they are chromosomes at the poles. And each cell divides into 2. So you end up by having 4 cells. So this one you have 4 cells. You have this situation, or that situation, or that situation, or that situation at telophase 2. So at telophase 2, you have 4 types of cells. You see, you have this one, you have AB, this one is AB, this one is AB. We don't have any other AB there. Then you have this type of cell, small a, small b. You have small a, small b here. You have another small a, small b here. So that's another type. Then you have big A, small b, this type. You have this one here. You have one here, big A, small b. You have another one here. That's type 3. Then you have small a, you have small a, big B. You have one type here, and then you have another type here. This is it. So you have 4 types. One can predict the number of possible combinations. For instance, this is the equation. The number of possible combinations of chromosomes or genes is 2n. The n is the haploid number of chromosomes. We started with 4 chromosomes and 2 homologous chromosomes. So 4 chromosomes, the haploid number is 2. Diploid is 4, haploid is 2. We ended up with 4 types of cells. You see, so 2 raised to the power to 4. So you see, we have 4 different possible combinations. And in human beings, we have 23 chromosomes, haploid number. So the possible combinations of alleles, we can have 8 million plus possible combinations. No wonder no 2 individuals are the same. Endless variation. When crossing over comes in, endless variation. We are going to use all that we have done to explain Mendel's laws. Mendel's first law is the law of segregation of genes. It states each character in an organism is controlled by a pair of genes or alleles. But during the formation of gametes, only one of the pair of genes or alleles goes into one gamete. So we are using this to illustrate Mendel's first law. He says that each character is determined by a pair of genes or alleles. So you have this character, big A or small a. This character stands for color. This one can stand for red color, and this one for white color. And Mendel is saying that in the formation of gametes, only one of these alleles go into one gamete. And our independent assortment ended up having big A in one gamete, small a in one gamete. Big A and small a are not in the same gamete. That confirms Mendel's law of segregation. That is Mendel's first law. We started with the other chromosome, big B and small b. These are 2 alleles. And Mendel says that in the formation of gametes, only this allele or that allele goes into one gamete. The 2 alleles do not go into the same gamete. And using independent assortment, we have proved that this big B and small b, they are in different gametes. Good. Now, Mendel's second law is the law of independent assortment of chromosomes or alleles or genes. And the law states that each member of a pair of genes can combine randomly with either member of a pair of genes in one gamete, provided the genes are not linked. That is, provided the genes are on different chromosomes. Now, we have also proved Mendel's second law, that is the law of independent assortment of chromosomes or genes, by what we have done. By Mendel's law of independent assortment, Mendel is saying that if you have this pair, this homologous chromosomes, this pair of genes, this chromosomes, this chromosome or gene can combine with either this or this in a gamete randomly. This one can go into the same gamete with this one can go into the same gamete with that. And he's saying that provided these genes or alleles are not linked. Linkage means that you can have this gene A here and gene A here and gene B and B. They'll be on the same chromosome and they are together. They are linked. And Mendel is saying that provided the genes or alleles are not linked, they will go into separate gametes randomly, not depending on any one of them. And we have proved that by using meiosis, we have proved to show that this gene or chromosome or allele will go into the same gamete with this or with that, randomly, not dependent. And that is what we have shown here, that you either have this going together, this going together with this, or this going. We have proved that. We have proved Mendel's second law. This gene came with this big gene here, not linked with small b or small a. Well, this is what we have for today. If you like the lessons, please give us your likes and please subscribe. Thank you very much. Bye-bye.